Hi everyone, welcome to our lesson on stereochemistry. The reason why we want to study molecules in 3D is because it's very cool. You know, we usually write molecules on a piece of paper and we just expect to behave that way. But in fact, they're three-dimensional molecules and they have different properties than just two-dimensional molecules. And it could even result in the difference between life and death. In fact, we like to study three dimensions because that's how molecules behave in the body. We have enzymes that are three-dimensional. They're proteins with certain shapes, and the molecules that are important for their function bind to them in certain ways. Some of them fit into active sites, some of them don't, some of them fit in a strange way. All of this has very interesting and very important, significant consequences to our bodies and the way that we function. So I'm going to start off with this notion that, we need to understand that three-dimensional characteristic of molecules. And I'm going to start by just starting with very simple molecules so that we can understand this better. Okay, so I've got a molecule here. On your page it says bromochloroiodomethane. Go ahead and build a model of it. So I've got it right here. So chlorine, iodine in purple, bromine in orange, and hydrogen here in white. And so you can see it's carbon with all different groups around it. And when I build a molecule just like it, you will see that they're identical because they have this ability to superimpose on itself. So these two molecules are identical because I can superimpose them and they match up exactly. So I know that they're the same molecule. They're not isomers, they're the same. So now what I want to do is show you an example of how the connectivity is the same, but I could have a different 3D spatial arrangement, just like we saw with cis and trans, but there's no double bond or ring in this case. So how do we get a different arrangement? Well, try taking one of these and just switch any two groups. And now all of a sudden when you try to superimpose, so you see my orange is together and my white is together. When I try to superimpose them, doesn't work. These iodine and chlorine and iodine, they don't quite superimpose on themselves. But there is a unique thing that happens, which is they look into a mirror and they see its reflection in the other molecule. So we call this a mirror image. So it's a molecule that has a mirror image which is non-superimposable. And this is the definition of a kind of stereoisomer, which we call an enantiomer. So they are clearly not the same molecule because they do not superimpose on each other, yet they have the same connectivity in that they have the same atoms attached almost the same way, but their 3D spatial arrangement is different, and it's such that they're mirror images that don't superimpose. So here I've drawn one form of this bromo, or actually alphabetical order, right? Bromo, chloro, fluoro, methane, okay? And it's looking into a mirror. And what would its mirror image be? Well, this fluorine in the back would see a fluorine in the back, and a bromine in the front would see a bromine in the front, chlorine in the back there, hydrogen would see itself right here. So if that mirror image was a molecule and you tried to superimpose them, they wouldn't superimpose. And this is very similar to how our left hand has a mirror image of our right hand. When it's looking into a mirror, it sees this, and they try to superimpose, but they don't. So they're actually enantiomers of each other, mirror images that are isomeric, not identical. So these are a type of stereoisomer. So what is it that makes certain molecules have that property of having these mirror images that don't superimpose? How come some molecules may have these stereoisomers and other molecules don't have stereoisomers? So that property is called chirality. A molecule that possesses chirality has a certain asymmetry, like our hands have an asymmetry. But a perfect sphere, it's completely symmetrical. So we would not say that a sphere is chiral, but we would say that certain objects with asymmetry have chirality. So examples of chirality that we often see in nature are things like left and right hands or left and right feet. Trees, where you see the branching patterns are very different on one side versus the other side of a tree. DNA, notice that anything that has a sort of a spiral, spirals in one direction. That could be DNA or seashells or things like that. Nature tends to favor one direction. So it's a very interesting property. Now with this molecule, what makes it possible for this molecule to have a left and a right-handed form? Well, there are certain patterns that we see. So for example, sp3 hybridized carbons often are centers where chirality occurs. And they tend to have 4 different groups on them, just like the molecule we saw here. So if you have that, then you're likely to have what we call a stereogenic center. And then we also can, switch 2 groups, and we see that there's a possibility for a stereoisomer. In this case, these are called enantiomers, which is sort of a hard word to say. Can you say it with me? Enantiomer. Okay? So get used to that. You're going to see a lot of vocabulary here. I tried to put them in bold, but try to highlight them and make a vocab list so you really understand what they mean. It's going to help you a lot in this chapter. All right, now these chirality centers often tell us whether there's a possibility for left and right-handed form. So for example, we were just looking at bromochloroiodomethane. It fits these 2 requirements of an sp3 hybridized carbon and 4 different groups. Remember, this is a methyl group right here, CH3. When you don't see a group explicitly on the end of a bond, it's a carbon with however many hydrogens needed to fulfill its octet. So these are 4 different groups, and so if you took any 2 of those groups and switched them, you would likely have its enantiomer. And you can try that. Draw, the bromine and the CH3 group switched, and you'll see that, oh, they can't fit on top of each other. And yet the molecule has the same formula, it's got the same connectivity, all 4 groups attached to 1 carbon, and yet 3-dimensionally it doesn't work out to be the same thing. So I'm going to work through this example with you. 2-chlorobutane, we're looking for an atom that is sp3 hybridized and has 4 different substituents. And what that will tell us is that there's a chiral center, just like we have here. And we usually denote that with an asterisk or a little star. Okay, so do you see any atom in here that is sp3 and attached to 4 different atoms? So this is CH3, so that's not going to be a chirality center. Here, this is a C with an H and a Cl and an ethyl group, which is different from the methyl group. So this is where our chiral center is, right here. And here there's CH2, so CH2 is got two of the same groups, 3 of the same groups here because it's CH3. So we have a chirality center here. So what that means is there are 2 possible stereoisomers. There's the Cl pointing out at you, and then there's the version with the Cl pointing back. And if you take this and try to put it on top of this, you see that the Cl's point in opposite directions. They don't superimpose. So they're not the same molecule, even though they look the same, right? That it's all about 3D. So wedges and dashes are very important in this chapter. You gotta know, is it pointing out or pointing back? Because that affects whether things superimpose or not. So these, are they mirror images of each other? Let's take a look at that. If I were to draw the mirror image of one of these, let's say this molecule is looking into a mirror and it sees its mirror image. Okay, well when I take this molecule and I rotate it, I'll get this molecule. And this molecule we already talked about doesn't superimpose with this one. These are different molecules. Therefore, these 2 are different molecules. So the mirror image of this molecule is this, which is the same as this, and they don't superimpose on each other. So the proper term is These are enantiomers of each other. They're stereoisomers. They're not the same thing. So what I want you to do is rewind that if you need to hear that again, first of all, because believe me, it took me a long time to figure that out. Okay, so don't feel bad. Should be all pretty new stuff to you. So what I want you to do in these two molecules is look at these two requirements. I say requirement lightly because they're actually not. You can have chiral molecules that don't have these things, but they're very few and far between. So go ahead and use these as guidelines and see if you can find stereo centers or chiral centers in these molecules. This one will have just a few, one or two, or something small. This one will have a lot. Okay, so go ahead and give it a try. When you find a chiral center, go ahead and put a little asterisk on that carbon. Okay. All right, guys, this molecule is naproxen, which is also called Aleve. It's an anti-inflammatory drug. It's really interesting. You'll see a lot of drugs that have a lot of stereochemistry, and that, again, goes back to that strong connection between 3D and how our bodies work with 3D molecules. So here, notice this is sp2, and then we've got this atom here. So there's four different groups here, and the rest are sp2. And even with these guys, these have resonance, so this is really like sp2, and this one here also has resonance, so that's like sp2 in a sense. And so usually we're talking about carbons, but chirality is not limited to carbon, but we will talk about carbon mostly. So we've got a possibility of stereoisomers because this is our chiral carbon here, and this carbon might have a methyl group sticking out at you, or it might have a methyl group sticking back. So those are the two stereoisomers, enantiomers of Aleve. In this molecule, it's really tricky because you've got this very complex, cholesterol actually is considered a small molecule, but for us, we're just learning OChem right now. This probably looks pretty big to you. All right, so here we've got 4 different groups, and I think it's probably the first time you're thinking of a ring as having one group going this way and one group going this way. And they're actually different because, picture you're writing this molecule here. You're going to see different things than if you go this path. So these are considered 2 different groups, even though they're tied together in a ring. Okay, so this group is one thing, this OH is another, this group is another, and this hydrogen in the back is yet a 4th group. So this is a chiral center right here at this carbon. This carbon is also considered chiral, and this carbon is sp2. Notice that the wedges and dashes are often places where there's chirality, like here, 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 here. But just be careful because it doesn't always lead you to the right answer. Like here, there's 2 H's, so this is not chiral even though it's wedged. So just be careful of that. 1, 2, 3, 4, 5, 6, 7, 8. 8 chiral centers there. Now every chiral center means that you have a maximum of 2 possible stereoisomers. So the more chiral centers you have, the more possibility of isomers you have. So let's take a look at this molecule had 2 stereoisomers. This molecule had 2 stereoisomers. This molecule has 2 stereoisomers. Why is that? It's because at this carbon, you could have one of the groups be wedged or one of the that same group be dashed. Okay, so you have those 2 forms. When you get to more chiral carbons, you're going to have even more possibilities because each of these centers could be inverted. So it's 2 possible when you invert here, 2 possible when you invert here, 2 possible when you invert there. So it turns out that there's this formula right here. So you have the number of stereoisomers possible. This is the maximum number possible, but you could have less than this, which we'll talk about later. You have n number of chiral centers. So 2 to the 1 chiral center here is 2 stereoisomers of this molecule. And that goes the same for all these because they all have 1 chiral center each. Here you're going to have 2 to the 8 power maximum possible stereoisomers. So that's going to be 256. All right. So because, you know, you can have any combination of either a wedge or a dash in these 8 positions. Now the body recognizes, you know, a very specific one, right? But, you know, in theory, you could have many different kinds. So if you have a stereogenic center or chiral center, you know, the asterisk, if you have that in a molecule, you're likely to be chiral, meaning you've got this property of having 2 stereoisomers for every chiral center. So let's take a look at amphetamine, which is the precursor to methamphetamine. So Breaking Bad fans out there, I know you're out there. I'm one too. So this molecule here, you know, do you see the chiral center is right here? So if we have a chiral center, we're likely to be a chiral molecule. So I'm going to put chiral here. Now there are going to be cases later where you can have chiral centers and be achiral, or not have any chiral centers and still be chiral, but we'll go over that later. For now, this is most likely to be chiral because it has a chiral center. So go ahead and try now using the term chiral if you see a chiral center and achiral if you don't. Alright guys, so we're back, and I just want to show you whether these molecules are chiral or not. This molecule is all sp3, but this carbon, which looks like it should be chiral, actually is bonded to 2 of the same groups, which is methyl. So this is achiral. There's no chiral center here. This molecule has a cyclohexane ring, so how to deal with that is to picture going around the ring this way. Is that the same as going around the ring this way? Do you see any different groups as you're passing through? No, you see the same thing. You see a chain of carbons, right? So these 2 groups are considered the same. So it would be different if there was a double bond here. That would be different than seeing single bonds this way. But for now, these 2 groups are considered the same. So even though these are different, this is achiral. This molecule does have a chiral center. Do you see it? Right here. So this is carvone. We'll talk about it again later. And this last molecule looks like chiral center should be here, but again, be careful. Dashes and wedges can be deceiving. This is a methyl group, but this is also methyl group. So it's got 2 of the same groups. That provides enough symmetry for this to not be chiral. Now I mentioned to you before that chiral centers means that a molecule is likely chiral, but not always. And I also said achiral molecules, which usually lack a chiral center, could also have exceptions. So here's that exception. Achiral molecules are symmetric in some way. So if you take a look at this molecule, let's zoom in. This molecule looks like it's not symmetric. Sure, here it looks like it's half a double bond here and half here. There's a carbon here, there's a carbon here. But look, there's a bromine on the left and a hydrogen on the right side. How is that symmetric? Well, if you build a molecule, let's say my hand is the ring, and I've got a bromine and a hydrogen, you're looking at it sideways. So you see bromine on one side and hydrogen on the other. Then clearly you can't say it's symmetric this way because these 2 sides aren't the same. But remember, this is in 3D. You have something going forward and something going back. So it's 90 degrees to the ring. These 2 groups are 90 degrees to this ring. So if the ring is in the plane of the paper or the screen, and you've got the bromine pointing at you and the hydrogen pointing back, you've got symmetry this way. So that's what this dotted line is denoting, is symmetry slicing through the bromine and the hydrogen. So if you slice through this way, half of the bromine sees the other half, half of the hydrogen sees the other half, half of the ring sees the other half of the ring, and you've got symmetry. So in this case, even though it looks like it could be chiral here, you've got the plane of symmetry going through the molecule. We call that an internal mirror plane. And then you can also say, well, this group is the same as this group, so it's not even a chiral center. So these are all examples of achiral molecules. they lack a chiral center, and they contain an internal mirror plane of symmetry. Here's the same thing. I would draw an internal plane going like that with the understanding that this line is slicing through the methyl and the hydrogen, which are pointing forward and back in the same plane. Okay? And here as well, the methyl group in the front, you're slicing through the methyl group in the back. They're being sliced through, so there is going to be symmetry. And if you don't believe me, go ahead and make a model of this if you can. It really does slice through. Now in these cases, this group going this way is not the same as this group going that way because of the placement of the double bond. So this is truly a chiral center, as is this, as are these. These are all chiral centers. So just take a moment and confirm that with yourself, that there are 4 different groups on each of these chiral centers. Now when you try to slice through with internal mirror plane of symmetry, you'll see that you can't. When you try to slice through, this double bond does not see itself over here, right? So there is no internal mirror plane. So we call that chiral because it is a feature of asymmetry, and these are achiral. Now there is a mix and match of this where, let's say you're a molecule with some chiral centers, but you also have an internal plane of symmetry. So let's take a look at these. So here, this molecule, if you look at this methyl group is different from the other groups. This group going this way is different from this group going that way because this one has 2 carbons before it sees a methyl group, and this has 1 carbon and then it sees a methyl group. So this is a chiral center, and this is a chiral center, but do you see the internal mirror plane of symmetry? So we can draw a dotted line. That means in this cis molecule, you have 2 methyls sticking up next to each other. You slice through, and these methyl groups see each other, right, across that mirror. So this one looks in the mirror and sees this one. So there's an internal mirror in this molecule. That means that the chirality cancels out. So these chiral centers sort of cancel out, and this molecule, even though it's got chiral centers, because of that internal plane, that wins. This is going to be a chiral overall. And I think that's a good analogy to dipoles. You know, remember how molecules can have dipoles, but if those dipoles cancel, overall the molecule's nonpolar? This is, I think it's very similar. You have chirality centers, but then if there's an overall symmetry, that renders it achiral. I'd like you to look at these molecules then and determine, do you see any chiral centers? And then look for an internal mirror plane of symmetry. Remember, chiral centers usually means the molecule's chiral, but as long as you have an internal mirror plane of symmetry, you're going to be achiral regardless of whether you have chiral centers. But if you find chiral centers, just practice and draw them in for me, and then write chiral or achiral. And show me the mirror plane of symmetry if there is one. Alright guys, so we're back, and it turns out that all of these molecules have 2 chiral centers, so I've shown them, and they all have an internal mirror plane of symmetry, so they're all achiral. The molecules that fit in this sort of weird space where we have chiral centers but there's internal plane of symmetry, they are called Mezzo compounds. So Mezzo. So that's a special term we use for this kind of case. So let's review really quickly. Chiral means asymmetric. There's a certain property that creates stereoisomers. And so if they are mirror images of each other, but not the same molecule, like a left hand and a right hand, okay, they don't superimpose, so they're not identical, then we call them enantiomers. That's the kind of stereoisomer they are. If they're not mirror images, then that's something else, which we'll later call diastereomer. Okay, but let's not worry about it right now. It's hard to say, too. Okay, achiral molecules, they can be any molecule that just simply lacks a chiral center. But it could also be a compound with chiral centers, but an internal mirror plane of symmetry. So that's meso. So it could be regular achiral, or you could be meso, where you also contain chirality centers, but you have that internal mirror plane. These are all vocab words that are very helpful. So learn chiral versus achiral. You know, get it in your head, which is symmetric, which is asymmetric. Enantiomer, meso. All right. So for practice, go through each one of these, show the chirality center with an asterisk, determine if it's achiral or chiral overall by also looking for an internal mirror plane of symmetry. Keep in mind there's going to be some cases where it's not so straightforward and you might have to manipulate the molecule in order to see an internal plane of symmetry. So usually that might include some kind of rotation. So we'll give it a try and we'll go over it soon. Okay guys, now we're back and I've marked all my chirality centers here. And I just want to show you that there's no internal mirror plane because this looked into a mirror and it would see another dashed one. And this was wedged and it would look in a mirror and see a dashed one. So they're missing each other in the mirror. They're not aligned. It would have to be cis in order to be a mirror plane of symmetry. So this is not meso. This is actually chiral. So if you draw its enantiomer, go ahead and draw the enantiomer of that is where you switch these groups. And try to put this on top of this one, and they don't match up. These methyl groups don't match up. So these are enantiomers of each other. So therefore, it's chiral molecule. Number 2, there's no chiral center. If you built a model of this, you could actually make it planar and slice right through it. That's the internal mirror plane of symmetry, which is hard to draw on a piece of paper, but there's no chiral center, and there's an internal mirror plane. So this is achiral. For number 3, we see 2 chiral centers. You can't slice through this way because this methyl and this hydrogen are different. So this is chiral. For number 4, I got a lot of questions about this one in class. I would redraw it in a way that's easier to see. So I just counted my up groups as being wedged. It doesn't matter as long as they're the same. And then your chlorines on the other side. You can see you can't really slice through it this way because the methyl group here is not reflected here. So there's no internal mirror plane. And in fact, these are chiral centers right here as well. So this is going to be chiral. So that's a good strategy to use, you guys. Okay, redraw the molecule in a form that's easier to see. It doesn't always work, but it's a pretty good strategy. Let's look at number 5. We have a chair, a methyl up and a methyl down. So I put a wedge and a dash. And you can see the internal mirror plane. And also there's a lack of chiral centers because going around this way is the same as going around that way. So this is achiral. This molecule looks like it could be chiral in the sense that this carbon, that this ring has 2 double bonds that way and 1 this way. But no, actually a benzene is considered to be like that. It's symmetric. These bonds are all spread evenly around the molecule. So there's a plane of symmetry going through benzene rings for sure. And then here, this is not a chiral center because of the 2 methyl groups. They're the same thing. So you can rotate it. You can remove 2 groups and it will still be superimposable. This is achiral. And don't take my word for it. You can build it yourself and prove it. All right, 7, these are chiral centers because a methyl, hydroxyl, a hydrogen, and then the rest of this molecule. It's going to be 4 different groups. And you can see the plane of symmetry though. So this is achiral, but this is what we would call meso as well. And finally, number 8 here, this is really tricky actually because you have, I don't know how many of you can see this. I drew an eye looking at the molecule sideways this way. So you would see a hydrogen down here and a chlorine up here closest to you. You'd see that the methyl groups were anti, staggered anti. Chlorine back here is right here, and the hydrogen up here is back here. Okay? So once you get a good sense of how to make this into this, try making it eclipsed so you can see if there's an internal mirror plane. And in fact there is. When you make it eclipsed, you can really force it to have to be looking into a mirror and see if everything aligns. If this looks into a mirror, it sees that. Chlorine in the back sees chlorine in the back. Hydrogen in the front sees the hydrogen in the front. So this has a mirror plane of symmetry. Now does it have chirality centers? Yeah, here 4 different groups in here as well. So this is what we call a chiral, and it's also called meso. All right, so clearly you're seeing the value of knowing what's chiral and achiral. Meso, how that all fits together. What is an internal plane of symmetry? How can you identify that? So practice with that, especially if you're having a hard time seeing it. Try to use a model kit if you can. It's super helpful.